We see it in almost every tech startup, the immediate push to build an architecture capable of handling millions of users on day one. But over-provisioning infrastructure before you have the traffic to support it burns cash fast. At its core, a load balancer acts as a traffic cop. It sits right between the public internet and your backend, taking every incoming request and cleanly distributing it across multiple identical servers. This distribution keeps any single machine from getting overwhelmed. But by adding this routing layer, you are taking a straightforward monolithic application and turning it into a complex distributed system. That complexity introduces a new set of problems. Added network hops increase your latency, you must configure continuous health checks, and your operational overhead instantly multiplies. The real challenge is identifying the specific inflection point in your company's growth that justifies taking on that operational burden. Deploying this tech prematurely forces you to pay for engineering problems you don't have yet. But wait too long, and your system will buckle exactly when you finally get the traffic spike you've been waiting for. Let's start with the absolute baseline. If you are launching a new application today, you can likely handle all your early traffic by routing it directly to a single, properly sized server. When traffic starts to climb, the simplest response is vertical scaling. Instead of wiring up additional machines, you just pay your cloud provider to double the CPU and RAM on the exact same box. By doing this, you completely avoid the headache of network routing. The trade-off is that you are building a massive single point of failure. If the server needs updating or the application completely crashes, users get hard downtime. If you need to distribute traffic to avoid that single point of failure, but you don't have the budget for dedicated load balancing infrastructure, your first option is DNS round robin. Distribution happens at the domain level. The DNS node systematically cycles through server IP addresses, alternating paths without inspecting packets. But DNS is blind. If a server crashes, it keeps firing requests into that dead IP address until you manually update the records. These early-stage tactics keep your monthly bills low and your architecture simple. But because they lack intelligent fault tolerance, they are not viable for systems that require high availability. Once your traffic volume hits a threshold where intelligent routing is mandatory, you face a major architectural split, choosing between a hardware appliance or a software application. Software load balancers like Nginx or AWS Application Load Balancer are flexible programs running on standard commodity cloud hardware. This approach shifts your costs to a predictable, pay-as-you-go operating expense model. If traffic surges, you can spin up new instances horizontally in minutes, and the entire setup integrates perfectly into automated infrastructure as code workflows. Hardware load balancers are physical boxes sitting in a data center, packed with specialized application-specific integrated circuits, or ASICs, engineered specifically for high-speed packet forwarding. Because they process traffic at the silicon level, they deliver deterministic, ultra-low latency. But that power requires a massive upfront capital expenditure, long procurement cycles, and if you max out the box, your only option is buying a bigger box. Software wins on deployment agility and cloud elasticity. Hardware remains the champion for predictable, high-volume throughput.
After deciding on the infrastructure, you have to configure how the system actually routes the traffic. This happens at either Layer 4 or Layer 7 of the OSI model. Layer 4 routing operates at the TCP and UDP level. It directs traffic based entirely on IP addresses and port numbers. Think of Layer 4 like a postal worker who sorts packages using only the zip code. It is blisteringly fast, but it has zero awareness of what is actually inside the box. Layer 7 operates at the HTTP and HTTPS level. It is content-aware, meaning it acts more like a concierge. It inspects URLs, headers, and cookies to make highly specific routing decisions based on what the user is trying to do. To do this, the system has to decrypt and deeply inspect those packets. This requires significantly more CPU power from your balancer, which inevitably introduces a slight amount of latency to the request. As your cluster grows with unequal servers, you need dynamic weighted round robin. It sends larger traffic volumes to powerful machines and smaller streams to weaker ones. But if a server CPU spikes, it instantly diverts the heavy stream to a healthier server. Advanced routing algorithms are incredibly effective at maximizing your hardware utilization. However, they only work safely if you invest the engineering hours to build a complex, real-time health monitoring system alongside them. As you build out these systems, it is easy to conflate load balancing with autoscaling. They are frequently mentioned together, but they solve different problems. The rule of thumb is strict. Autoscaling dictates when to spin up new servers and how many you need. The load balancer dictates exactly where the traffic flows among them. If you implement autoscaling without carefully configuring your cooldown periods, a brief traffic spike will trigger a panic loop. Your system will rapidly spin servers up, charge you for the compute time, and immediately tear them down before they even process requests. Finally, as your application breaks apart into dozens of microservices, you introduce the service mesh. This tool is built specifically to manage the internal east-west traffic and retries between your own backend services. A load balancer is built to manage the chaos coming from the public internet. A service mesh is built to govern the complex internal chaos you create inside your own infrastructure. The final architectural decision relies on matching the specific tool to your team's current budget and risk tolerance. This scorecard matrix maps out that exact alignment across 3 distinct engineering profiles. For the bootstrap builder watching your burn rate, skip the load balancer entirely. Rely on vertical scaling or managed platforms until a few hours of downtime actively costs you more than hiring another engineer. For the growth engineer, your priority is surviving unpredictable viral traffic spikes. Deploy a Layer 7 software load balancer paired tightly with autoscaling, prioritizing OpEx flexibility and rapid horizontal growth. For the enterprise architect managing mission-critical systems, you need a hybrid model. Deterministic Layer 4 hardware appliances sitting at the edge, routing down to Layer 7 software proxies, while a service mesh handles your internal microservices. The most common mistake engineers make is giving in to the urge to build for the massive, hypothetical scale they wish for on day one. Optimal infrastructure design requires discipline. You have to build exclusively for the scale you have today, while maintaining a clear, realistic upgrade path for the traffic of tomorrow.